Okay, so hello everyone, my name is Arthur. I am a research engineer at Zeta-Alpha, where I'm working for the last 1.5 years on creating embedding and fine-tuning embedding for customers and for long-term users, and some research on how to improve embedding models in multiple scenarios. Today we're going to talk a little bit about how do we fine-tune models. Is it working well, everyone? Yes. Okay. We're going to talk a little bit about how to fine-tune embedding models, why do we do it, and we're going to talk a little bit about one of our last public models that we have released. I think it's our first mainline embedding model that we public, based on the 7 billion parameter model. It's quite good. We'll talk a little bit about how we created it, with data we used, and how do we fine-tune it, and how good it is. Cool. So I'm not going to spend any time talking about RAG. I think everyone already know what it is, like it was a really good job starting with it. So it's graceful, but everyone knows how RAG system works. You have about embedding, etc., etc. Spend a lot of time doing this animation, so I want to show off anyway. But it's, well, everyone knows what a RAG application is, at least in theory. In practice, well, a little bit more complex than that. Right? You have a lot of moving parts, a lot of things that you want to fine-tune, and to change, and improve, and to measure, etc., etc. So this is an example of our every moving RAG pipeline inside Zeta-Alpha to some of the components within it. But however, embeddings are cool, embeddings are amazing. They do a lot of nice things. They do factor search, a lot of matching of long syntax set matches. So if you have words are not the same, but they are semantically similar, vectors are really good for that. But it also fails really miserably in some examples. So these are, I mean, kind of spoiler, but these are 2 examples in our own Zeta-Alpha platform. If you query what is InPars, if you query something like what is InPars, is one of the things that we're going to talk about a little bit later. You can get 2 different results depending on what you're using. Kind of already spoiled it, but which one do you think was made using semantic search with vector search? Which one was made using keyword search with B5? Who thinks the left one is vector? Who thinks the right one? Who thinks the left one is vector search? Who thinks the right one is vector search? Good to know that is. And not for people know which one is which. Cool. So, which one is vector? The right one is vector. It's failed miserably. The left one is keyword. Vector just cannot find the same, cannot find InPars. So the question is, why is it so bad in this example? For us, it's just one example. We know it's going to fail as well. Some of the reasons is tokenization, out of vocabulary, and out of domain. So if this is one example of how it will tokenize this what is InPars queries. It will break down InPars into 3 different parts. So 3 different tokens. Each one of them should have its own meaning, and it's really hard to create an embedding on the thing breaking down, and especially because now it's very likely that your model has never solved this. So it's an out of vocabulary terms, so your model that have no idea what InPars is out of domain, so probably your model was trained on generic text, and InPars really specific keyword, specific term to this domain. So it's a thing that your model never saw before. So that's why this is one of the best reasons why you want to look into at least experimenting with fine-tuning your embedding models, instead of just grabbing something off the shelf and running with it. The main objective when you're doing something like this is to get the query embeddings, so this green, blue angle, and move it closer to your relevant documents, and at the same time take the query embedding away from non-relevant documents. So you were essentially, if you imagine vector space 2D, you were trying to move things that are not relevant away from each other, and things that are similar closer to each other. And a secondary objective here is essentially what we have talked about, learn domain-specific terminology. If your embedding model was not trained initially for search, well, we need to learn some of the search-specific parameters as well, how to do a match between terms in the search system. But then one of the hardest questions is, okay, I don't have data, I don't have any query data, it's a new system, I don't have any queries, I don't know what users are going to use it for, what do I do? Well, here comes InPars, what I mentioned before. InPars is a paper that I published a few years ago, 2022, 2023, on creating synthetic data for your domain. So again, this is public, this paper is published, the code is open source as well, you can look at it. And we use it quite frequently internally as well. The problem is that user queries are expensive to gather, so user time is really expensive, really hard to get. But you have a lot of data. You have your corpus there as well. And you're going to create queries based on the documents already there. So one of the really important steps here is to have some future input. So maybe you want to manually create some queries, and you're going to add these queries and the document and some random document from your corpus, and feed this to an LLM. Originally, it was not an LLM, it was a T5 model, but now we scale this up to larger models, of course. And you're going to ask this LLM to create for you queries that are likely that the users will use to find these documents. So there's a little bit of a twist on the LLM logic, where you would have a question and you have to create the answer. Now we're doing the opposite. If you do an answer, the document, you have to create a question for that answer. And so after some tutoring and some selection, you essentially create a considerably large collection of pairs of grid document pairs to fine-tune your embedding model. So this is one of the things that we see more frequently in our customers, that they come and say, oh, we have all of this collection, millions, billions of documents, but it's a new thing, we have no user queries, what do we do? Well, this is a good starting point. Of course, we have a large collection of user queries, and the data is curated. That's probably even better, but if you don't have queries, this is a really good starting point, and usually it works really, really well. So when you collect this large amount of data, there are a few. It's not as straightforward as just, I have the data, and what? You do some steps of filtering selection, gathering hard negatives, so for each query, document have a positive, and have hard negative samples as well. There are the wrong documents for that query. We have our own fine-tuning library that is being slowly moved towards sentence transformers. I'm going to talk a little bit about this a little bit later. To fine-tune this model, and we serve these models using Fast API in our own implementation in-house. But if you're doing your own thing, well, you can use whatever you want to serve these embedding models as you wish. Again, I encourage you to looking towards that, looking to sentence transformers library in GitHub. They have all the tools for fine-tuning your model as well. Cool. Does it work? Well, it does. Otherwise, I would be talking about this here. So there are just 3 examples that we have done this for real customers on real data, and improvements that we got from that. So we have examples on the capture domain, on the HR, and on, this is the one that have the name of the domain here, at the white on the legal domain of their own document as well. So in all of these settings, the clear ones, this one is the legal domain. We have a baseline model that is just whatever embedding model they had before, just by moving to a more modern embedding model like E5, so it could jump, fine-tune the model, critical jump, especially on non-English documents. That was a really important use case here. Our ranker, fine-tuning that, and then an hybrid search on top of that, so K25 and keyword, even further boosting the final performance. So in all settings, that fine-tuning your embedding in your domain should help considerably. Cool. This is usually talking about relatively small models, right? So we talk about E5 base, something like 300 million parameters, maybe even less, 100-something million parameters. Now we have considerably larger models and better models, so what can you do? Well, there's a new trend recently to create embedding models from really LLMs, from 7 billion parameters, sometimes even larger. Use these to create your embedding, so not just using an encoder-only model like BERT-based thing, but rather using decoder-only like GPT-based or YAML or whatever. The idea here is to essentially, I'm not going to go deep into this, but if you know what this is. This is a decoder block of a transformer. We're going to grab the last layer here of the embedding, so we have a different one embedding for each token. For input token, we're going to do pooling here, so grab the average of these, or the first or the last token. Then you grab the final embedding for the sentence. Essentially, what we are ignoring what makes LLM so cool. Like, we don't care about the output. We just care about the input. We kind of don't care what the LLM is trying to tell us back. We just want to see what it thinks about it, about this input. So with this approach, we have here our first public embedding model. There's the Zeta-Alpha-E5-Mistral model. So it's our first open embedding model. It's based on E5-Mistral. It's already based on Mistral. It's a 7 billion parameter model. We trained this on 30 data sets. Essentially, it's a mix of 30 different data, about 1 million training samples in total. We use a technique from NVIDIA of sampling hard negatives. It took us about 8 hours and 4 times 800 GPUs for fine-tuning, so about $1,200, so it's not very cheap for fine-tuning, but also not absurdly expensive either. The training recipe and the model are public. This is the MTAB leaderboard. I don't know, is anyone knows what the MTAB leaderboard is? Okay, more than I thought. So the MTAB leaderboard is a leaderboard of embedding models on multiple tasks. So anyone can submit your model and evaluate on a bunch of different tasks, a bunch of different data sets. Then they have a ranking of the last models. This model got number 8 on ranking, on the retrieval portion of the benchmark, which was basically our goal to start to get on the top 10 on our first public model. Yeah, so it's actually quite good. It's a good retriever, it's a good embedding model, to be honest. We have blog posts about it. We all the details of the training recipe, the data we use, how to use it, etc., etc. A little bit about the data that we have used to train. As I mentioned, there's 30 different open data sets, so all data that we use is public, nothing is private, everything is openly available. We have all of the links in the blog post as well. It's about 1 million samples from retrieval data sets, classification, and clustering data sets. We were quite careful to avoid using test samples in the training, leaking these two things, so we're not cheating. You're seeing the test data in the training data. Something that's really important is to get the hard negatives. So we mentioned about the NVIDIA thing to create hard negatives. That also was really important to have 7 hard negatives for each query to avoid false negatives as well. Some training details. Well, we tried a lot of different combinations of data, hyperparameters, etc., to get the final model. These are actually the loss of the different runs that we have tried. How the evaluation evolves over time. So the blue lines, the models that have actually a release. The green and the purple line are models that are currently under development. Secret. Hopefully going to be public soon. We use LoRa adapters to fine-tune it, so it's not fine-tuning the whole network, just the adapters. A progressive loss with algorithm caching is a technique for improving the bets or have really large batch sizes. Something quite interesting to do, they have instructions, so you're not embedding only the query, you're adding some prompt engineering, quote unquote, to the queries before you send that to the model. So you have to like retrieve, giving this question, find relevant documents, or something like that. So that's what you're actually embedding, not only the query text itself. We use our own PyTorch script for doing this, but Most of the adaptations of the big script are now part of the sentence transformers 3.3 that was released yesterday, I think. So including this instruction training, all that, so we all put it back to the sentence transformers code to be open source now. So these are some plots of the training with instructions from the newer sentence transformers release that we were working with, helping with the Thomas from sentence transformers to do this, to make this public. Another thing that was quite cool that we did for this model is the NanoBEIR dataset. The problem is that when you're training a large model like 7 billion parameters, an evaluation run can take a week. You don't want to be sitting waiting a week to see if your model is good or not. It's boring, wasteful, etc., etc. So we created this NanoBEIR dataset collection. There is a sample of the BEIR dataset, or like a collection of retrieval datasets for benchmarking models. We sampled 50 queries from 50 documents and up to 10,000 documents in each. And the evaluation time dropped from 1 week to a few minutes. So now it's kind of feasible to do this while we were training to validate your model actually improving as we trained it. And it was also added to sentence transformers this week. So we can quickly use the same thing that we use for evaluation. The data set is on Hugging Face, all the data are on Hugging Face. Now it's part of sentence transformers as well to evaluate these models quickly. What's next? Well, there's a burning question of, okay, 7 million models, cool, powerful, but not very practical in most cases, right? 826 gigs of memory in full precision. There are things we can do to improve it. For instance, optimization of the embeddings and of the model itself to make it smaller, to make it run faster. There is now a really nice trend of smaller LLMs, so they're quite good. Maybe not with 7 million, but maybe enough to be really good embedding models. It was kind of a run with Llama 3 with 1 million parameter, then Quen with 0.5, and now Hugging Face has a 135 million parameter model. It's tiny in comparison. So it's possible that this could be a way out of this problem of really large models and practically using them. Well, this is closer to OpenSearch. How do we score this? One 7 million model has 4,000 dimensions for each embedding. That's quite a lot. OpenSearch 6.2.17 has binary organization and disk-based search that we have actually experimented with this quite recently, like last week, this week, and how the latency changes on multiple benchmarks and even the quality of the retrieval, how it changes. Well, our experience is that since 2.18 is quite good. So this can drop considerably using the disk-based with a quantization of the embeddings. Can be a really interesting way out. And it's now 2.18. There was a bug in 2.17, now it's fixed in 2.18. It's quite good. And finally, languages. Well, this is mostly for English. We are in Europe. There's multiple languages here. That maybe no one or almost no one here is native English speaker, right? So how do you do this in Dutch, in German, in Spanish, in Portuguese, etc., etc., etc. There are data sets, there are starting to have models based on this. That's still quite new. It's also another frontier that we're looking into. How can we help with creating really truly multilingual embedding models? Okay, I think that's it. Try to speed run through the slides in a minute. Cool. Any questions?